Welcome to Lesson 5, example number 3, and is asking to select the reinforcing seal with given the data. And the first thing we want to do is you want to figure out what is your load. So they give us the service unfactored, I guess, dead load moment and live load moment. So we want to figure out the ultimate moment. Mu equals, and our factors are 1.4 dead load, 1.7 live load. And tell you what, let's see if they say where they got that from. Well, I don't see it on top of me. I mean, right away, I don't see where it is. So I'm just going to go ahead and assume that that's all right. Properties of concrete. All right. I feel a lot better. And tell you what, maybe next video I'll tell you where they're getting this 1.4 MDL plus 1.7. They maybe get it from the UBC or IBC or something like that. I'll go get my ASCE book. Actually, I'll do that right now. I'm looking at my ASCE and it basic load combinations. And they have combining nominal loads using allowable stress design. Actually, I have the ASCE 7-98, which means it's 98 was when it was made. And they have basic load combinations, and then basic load combinations for allowable stress, and then they have basic load combinations using strength design. And it doesn't match up. It's like, well, it looks like 1.2 dead load plus 1.6 live load. So I'm not sure exactly where they're getting this 1.4 and 1.7, but we'll just assume that that's okay. Anyways, we're moving on. So we were going to go ahead and figure this out. Mu equals 1.4 dead load, which equals 80 foot kips, plus 1.7 live load, which is 115 foot kips. And let's go to the calculator. 1.4 times 80 plus 1.7 times 115, and you get 307.5. Remember, that's ultimate factored moment, and however you want to call it. I call it ultimate moment. Alright, and now we want to, let's go back. I actually paused it and I'm continuing from last evening, so it's the next morning and I forgot what we're looking for. So the reinforced concrete beam must resist a dead load. Select reinforcing. Okay, so we have I'm assuming it's a rectangular beam, and they gave us B12, so that's going to be 12. Remember, here's your steel. And we don't know how much steel it is. And that's what we're solving for. We're designing for steel, but they gave us this D. And D is 32 inches. And now we need to select the reinforcing steel. And there's, I guess, a few ways you could do this. But, well, you could go in and say, more do a plug and chug and use this equation again. This phi mn equals phi as fy d minus a over 2. You could use this and just plug in. Let me think what we have. We know this is 0.9. The area steel we don't know, so we'd have to solve for that. Fy equals 60. D we have. A we don't know. They don't do it this way, but one thing you can do is you can just say A equals, I'm going to do it this way first, and we'll do it the way they do it in the study guide. A equals, sometimes you can say A equals 0.1D, and this is approximation. And you'll find out a lot of times engineering is not as exact as you'd like it to be, and that's alright. So you just say, oh, okay, well, A equals 0.1D. So if we do that, if we say that, it's A, let's say A equals 3.2. Equals, say, 3.2. And when I say, that means just that it means it's not actually. It's just your guess, your approximate. All right, so let's go ahead and throw that in there. And we need to solve for, we need to substitute mu. I guess that's our minimum phi mn. So let's go ahead and throw that in there. And I changed colors again. So we're going to substitute phi mu, or mu for phi mn. Foot kips equals 0.9 for phi. AS, we don't know. That's what we're going to solve for. 60 KSI. D is 32 inches minus 3.2 inches over 2. I have a bad habit of trying to put 12 there. And then we divide by 12 to make it foot inches. And then I'll go ahead and do that. Inches, foot. And that will give us, me doing this, took it from KSI. You see we have inches, and that changes that to get the kip foot over here. And we have KSI, so we're going to be kips over here as well. So let's go ahead and solve for AS. Your area of steel, and that's going to be your minimum area of steel. Because you're saying your minimum area of steel to get this, so anything higher area of steel we go, it will be higher than mu, which is what we want. Alright, so AS is going to stay over there. So we go 307.5 divided by 0.9 divided by 60 divided by 30, open parentheses, 32 minus 3.2 divided by 2, close parentheses, times 12. And we get 2.25 inches squared. And let's see if that matches up with what they got. They have this they use this other equation where it says mu over phi fy jud equals 2.37, and we got 2.25. So there, it's close to being about the same. And let's go ahead and look about what would be good for this. Let me go back to page, I forget what they have the reinforcing on it. Here it is. It's page 87, and let's look around and see how can we get 2. There's probably a bunch of different ways you can get 2.25, and they use 2 number 10s, and that area of steel equals what? 2.54. So it's 2. Sorry, I'm just going to go ahead and write it out. 1.27 inches squared. And that's on page 87. I think I said that, and that's under the ASTM standard reinforcing bars. You can find this on a bunch of websites. There's also some cards that they put out, and that's going to be 2.54 inches squared. And that's greater than this, so we could use that. You could also go in and use 3. Let me think. You could use 3 number 7s. So 3 times 0.6 equals, no, that wouldn't work. You could use 4 number 7s. 4 times 0.6 equals 2.4. And there's a lot of different ways you can do this. Let's see if they justify why they chose to do 2 number 10s. And it says select the reinforcing steel from, okay, it doesn't give a reason why they chose 2 number 10s, but typically what I'll do is, let's say you have I guess this will be fine. The 10s are pretty big reinforcing steel. That's probably about as big as you want to get. I've never used anything larger than an 11 in this type of beam. Sometimes you use bigger for columns. But number 10s are getting pretty hefty. I mean, that's a bar that's what? You go look on page 87, you can see that it's, what, pounds per foot? It's getting 4.3 pounds per foot. So if you have a really long bar, that's a pretty hefty size. But typically what you'll want to do is, I don't think they've talked about minimum clear distance, and that's a big deal, because if you put the bars down here, they're going to pop out. They'll pop out like that. and you will fail. So typically, I think the minimum clear distance that I have typically seen is 1.5 inches, and a lot of people just use 2 inches clear, and that means clear distance from the outside edge of the bar. And then when I say clear distance, I mean here to the edge of concrete. It needs to be what usually it could be easy. You just say 2 inches, or sometimes a lot of times what I'll do is just say from, I mean, just for spacing issues, you can just say, oh, from the middle, make it 3 inches from center line of the bar to the exterior. And it kind of depends what you're doing. That might not always be the case, but you want to do that. It's kind of engineer's judgment, and you'll get there once you do a lot of design. All right, so in this case, let's think about this. I would say let's assume it's 3 inches from here to here, 3 inches from center line to exterior. So that's 6 inches, and you have 6 inches in between. 6 inches, 3 inches, 3 inches. And you know what? That doesn't seem too crazy. So I would go ahead and say, yeah, 2 number 10s is fine. A lot of times, if you want to do more, like if you want to do 7 number 4 or something like that, they wouldn't fit in there. You need a certain, and you'll look into like the ACI manual, you need a certain distance of spacing, and I really wouldn't get anything, hi Liam, I wouldn't get anything lower than like 5 inches. And there's some rules, like you want to stay a certain amount of bar lengths. Really, anything you get under 6 inch spacing, it can start to get a little bit of shady. So I would stay over 6 inches. But all right, Liam's helping me out. Liam's my 2-year-old here, and he's wanting to play with my pen. So give me a second. Hold on, sweetie. Here, play with this. All right, so I did it the way I guess I feel comfortable with doing it, is an approximation. And another way to do it is, if you go back on page 89, you can see how they say that the moment arm, D minus A over 2, is sometimes referred to as JUD, where JU is approximately 0.9, which is kind of the same thing I was doing if you think about it. I was saying it was 0.1, but let's go ahead and do it that way. So let's use the equation. Let's use the equation. AS equals MU over phi FY JUD. Remember, we're assuming, and that's assuming JU equals 0.9. We know FY, we know phi, we know MU, so let's go ahead and just solve. AS equals MU, which we had was which was 307.5 foot kips. And then this is 0.9. And we're probably going to change this into, yeah, because we want inches, so we're going to have to change this to inches as well. And that's, what, 1 foot equals 12 inches. Sorry, it's a little bit cockeyed there. FY equals 60 KSI. JU equals assume 0.9. And then D, we knew, was 32 inches. And what we get is 307.5 times 12 divided by 0.9 divided by 60 divided by 0.9 divided by 32. And none of that worked. Let's try again. 307.5 times 12 divided by 0.9 divided by 60 divided by 0.9 divided by 32. We get 2.37. And that's somewhat close to this. These are both approximations. And what you can do is you can actually go back in once you decide on your steel, and if you feel the need, you can go back in and, you know, figure out what your A is using AS. Now you now know FY over 0.85. F prime C B, and you know all those get you A, and then you do the phi MN equation to get